Hey pre-calc students, just wanted to make a video about vectors in the plane space. This is an introduction video on what vectors are. So before we can talk vectors, we're going to first talk scalars. So a scalar is any quantity that has a size. So for instance, like a temperature, a distance, height, area, volume, all of these are represented by a size value or a number. This is called a magnitude or size. These quantities are again called a scalar, and an example of that is 60 miles an hour. So if you're talking speed, speed would be considered a scalar. A vector is similar to a scalar, but it has a new component to it. So the quantity 60 miles per hour to the northwest is what's called a vector because it has both size and direction. So vectors are quantities that have both a magnitude, which means size or length, and a direction, which we usually refer to as an angle. Vectors are represented in the plane of space as an arrow. So we have an arrow, and that's representing some kind of length, which is the magnitude, and then the direction showing the arrow kind of in the direction that the angle or that the arrow is pointing. These types of things are force, velocity, and acceleration, and these are things that can be described as vectors rather than just scalars. A couple different ways to notate a vector. There's point form, component form, and then what's called a unit vector addition. I'm going to draw a vector and then we'll talk through some ways that we can talk about or notate a vector. Okay, the first way to talk about the vector is in what's called point form. So again, the point form is describing an initial point and a terminal point. The initial point is marked as the start of the arrow. And in this particular case, I have an initial point P, which is marked at -3, 1. My terminal point is the point that shows me where the end of the arrow is going, where the arrow terminates, and this is point Q at -1, 2. To display this point, this two-point system as a vector, we'll write this as P, Q, and we'll draw a little vector over top of it showing P to Q. A component form of a vector looks at the same vector, but just centers it at the origin. So I'm going to copy this little vector, and I'm going to slide it over to the origin. The component form of a vector takes just the end, because if it's component form, understanding that it's at the origin, starting at the origin is understood, and you write it as the terminal point. So here, this terminating point is the point 2, 1. And so to write this in component form, we would say this is the same vector at 2, 1. We're using angle brackets instead of parentheses. This shows that it is a vector and not just a point. So again, the point is talking about the terminal point, and then the angle brackets is what makes it a vector, connecting it to the origin as the initial point, and the point 2, 1 as the terminal point. These two are two different ways of describing the same exact vector. One is just located attached to the origin, and the other one is not. And then the other way to write a component form is what's called a unit vector addition. And this just goes back to textbooks and saying which textbooks prefer. Most textbooks are going to prefer your component form, but every once in a while you'll see what's called a unit vector addition, and that would be the x component marked with an I plus the y component marked with a j. These are pretty much the same thing, the component form and the unit vector addition form. It is just all about which textbooks prefer. Again, the component form is definitely the preferred one, and I think the one that Delta Math uses, but it's also important to know the other form as well. Again, I and j are just labels, labeling the x component and the y component. To convert point form to component form, all you have to do is take the terminal point and subtract the initial point, and that will give you your component form of your vector. So for example, I've got if u is the vector with an initial point p at 1, 2, and a terminal point q at 5, 7, we want to find the component form. Well, we can draw this and then move it, or we can just do our subtraction. So we're going to take our terminal point, 5, 7, and we're going to subtract our initial point, 1, 2. To subtract points, we're just going to subtract the x values, and then we'll subtract the y values. So the x value 5 minus the x value 1 gives us an x value of 4. The y value 7 minus the y value 2 would give us a y value of 5. And now, because this is a vector in component form, I'm going to use my angle brackets to show that this is a vector and not just a point. I could have also written this in ij form if I wanted, 4i plus 5j. Again, either of these forms is talking about the vector that is the component form of a vector that is starting at the point 1, 2 and ending at the point 5, 7. We use the word magnitude of a vector to describe the length or size of the vector. This is notated with a set of absolute value bars around a vector v, or a double absolute value bars. Again, it goes back to different textbooks or websites use different notation. The formula to find the magnitude is just Pythagorean theorem, because again, we're finding a length, and so we're going to treat that like a hypotenuse. So if I wanted to find the magnitude of the vector 3, negative 2, the first thing I'm going to do is draw this vector. Okay, I've drawn this vector. Since it's in component form, I started it at the origin, and it points to the point 3, negative 2. And to find the magnitude or the length of this vector, I'm going to take the square root of the x value squared plus the y value squared. Okay, and so what I'm describing in the magnitude is how long the vector is. Again, the magnitude is describing some type of length or size of the vector. So this vector has a magnitude of 3.6 units long. Another way that we can describe a vector is the direction. We use angles to describe direction, and the precise way to do this is to talk about the angle that it makes with a positive x-axis. We call this angle theta, and you can almost think about it as the unit circle angles. So if it was pointing, on the x-axis, we would call this 0. If this is pointing on the positive y-axis, we would call this angle 90 degrees. Negative x-axis 180, negative y 270, and then again, if it was pointing back here, we could also use the angle measurement 360. To find the angle measurement, we'll need to know that the tangent of any angle measurement can be found by doing y over x. Okay, for an example, we're going to find the direction of this vector, but in addition to the direction, I want you to see if you can draw the vector and find the magnitude on your own. Then we'll do the direction angle together. Okay, so I've drawn my vector, and I have my magnitude, which is 5.1. Now we're going to talk the direction angle. Well, similar to the way we were finding polar angles, or the way that we were finding a angle in any trig on the unit circle, we know that the tangent of an angle is equal to y over x. So in order to find the angle measurement, I need to do the tangent inverse of the y value. The y value of my component is 5 over the x value 1. We'll use our calculator here, and I would encourage you to do this calculator in degree mode. Rounding to the nearest whole number degree, I'll get 79 degrees. So we can also not only describe how long the vector is. This vector has a length of 5.1 units long. It also makes the angle of 79 degrees to the positive x-axis. Because the tangent inverse has a limited range, sometimes you're going to need to fix the direction angle. First, I want you to try to pause this video and do as much of this as you can. Find the direction angle, and again, not the magnitude, but just the direction angle for the vector -8, -4. Okay, so this is saying that this vector is happening at the angle measurement of 27 degrees. If you remember, if this is 0 degrees and 90 degrees, 27 degrees is happening somewhere in here. And what's actually happening is because this angle measurement was a negative angle, tangent inverse did a little bit of simplification before it applied the tangent inverse. So this is actually treating this angle measurement like it was going to +8 and +4. So it's in the wrong quadrant. And we talked last unit about how to get to the right quadrant if your tangent inverse tells you that you're in the wrong one. So here, if I am at if I'm at 27 degrees in quadrant 1, and I need to go to a vector that is in quadrant 3, I need to go 2 quadrants away, so I can always add 180 degrees. Adding 180 degrees puts my angle measurement at 207 degrees. And this makes a little bit more sense because that is between 180 and 270. Sometimes a vector is described in magnitude and direction. So then we have to find the component form. For example, down here, we want the component form of the vector with an angle measurement of 120 degrees and a magnitude of 8. Essentially what we're doing is we're finding the x component and the y component. And you can think about this as a length and this as an angle. And again, this kind of goes back to what we were doing with polar points. If I have let me draw this first. So if I've got this magnitude of 8 and I'm at the angle 120, to get the vector form or the component form of this vector, I really need the x coordinate and the y coordinate. To find the x coordinate, we're going to take our magnitude or our length times cosine of our angle measurement. And to find the y component, we're going to do our magnitude times the sine of our angle measurement. We'll use calculator values for this. And this will put my x value at -4 and my y value at 6.9. So I can write this vector in component form at -4 and 6.9. Okay, the last thing that we'll talk about is some vector operations. Two basic vector operations are the addition of two vectors or a scalar multiplication. To add two vectors, you're just going to add their two components, so the x component and their y component. To multiply a vector by a scalar, you're going to think of it like distribution. You'll multiply both the x and the y by the scalar multiplication. So we'll finish with two examples. The first example is I have vectors u and v, and I'm going to find the component form of u plus v. So just kind of very basically what this means is I'm going to add my two x components together, -1 and 4, and get 3. And I'm going to add my two y components, 3 and 7, and get 10. Okay, I'm going to show you guys what this looks like graphically. So the first thing I want you guys to do is to take a second and see if you can sketch a graph of both u and v. Okay, so what happens when you visually add vectors is I have vectors u and v drawn, and essentially what's happening is you're taking one vector, and so I'm going to take my v vector, and I'm going to add it to the tail end of the u vector. And what this does is it creates a new vector that starts at the origin and now goes to the point 3, 10. So 3, 10 is this new coordinate point, and so we get the combined vector of 3, 10 by adding our two components together. Okay, the last example that we'll do is a scalar multiplication. So for instance, same vectors u and v. I want to find 3 times v. To find 3 times v, I'm going to find 3 times both the x component and the y component. So I'll do 3 times 4, and I'll do 3 times 7, and simplify. Visually, what that looks like is you're taking a vector that was originally oriented to 4, 7, so the component form 4, 7, and you're copying it and doing it 3 times. And that gets you the vector 12, 21. See if you can try the last operation on your own, and then pause the video at the end to check your work.